When Richard Feynman said that the deepest mystery in physics is not quantum mechanics itself, he was quietly overturning one of the most common assumptions people have about science. Most of us believe that the mystery of physics lies in its complexity: strange equations, abstract mathematics, invisible particles, and counter-intuitive rules. We assume that once the math is mastered, the mystery disappears. Feynman's keynote challenges this belief at its core. He suggested that even when the mathematics works perfectly, even when predictions match experiments to astonishing precision, the real mystery can remain untouched. The shock is not that nature is complicated, but that nature refuses to explain itself in the way we expect. For centuries, physics progressed by building pictures of reality that felt intuitively satisfying. Newton's laws made sense because they aligned with everyday experience. Objects moved when forces acted on them. Causes came before effects. The universe behaved like a giant machine, predictable and objective. Even when the math became advanced, the underlying story was clear. A planet orbits the sun because of gravity. A ball rolls because it was pushed. Reality existed independently of human observation. Physics described what was already there. Quantum theory shattered this comforting picture. Yet many people think the mystery lies in its technical difficulty. They imagine that quantum mechanics is mysterious because it uses strange symbols or advanced calculus. Feynman argued that this is a misunderstanding. The math is not the deepest problem. Physicists can calculate quantum behavior with extraordinary accuracy. They can predict outcomes to many decimal places. The equations are not broken. What is broken is the story we tell ourselves about what those equations mean. This is where the challenge to common belief becomes profound. We are used to thinking that science explains reality. But quantum mechanics does something unsettling. It predicts reality without clearly describing it. It tells us what we will observe, but not what exists before observation. When Feynman called this the deepest mystery, he was pointing to the uncomfortable gap between prediction and understanding. We know how to use the theory, but we do not know how to think about it in ordinary human terms. The challenge becomes clear when we consider how deeply rooted our intuitions are. From childhood, we learn that objects have definite properties. A cup is on the table whether we look at it or not. A car has a position and a speed even if no one measures them. These assumptions feel so obvious that questioning them seems absurd. Classical physics reinforced these intuitions and turned them into scientific principles. Quantum mechanics, however, does not respect them. According to quantum theory, particles do not always have definite properties. An electron does not possess a single, precise position until it is measured. Instead, it exists in a state of probability, spread out like a wave. This idea alone is deeply disturbing to common sense. But the mystery goes even further. The act of measurement itself appears to play a role in creating the outcome. Observation is not passive, it participates. This directly challenges the belief that physics describes an objective reality independent of observers. In everyday life, observation simply reveals what is already there. In the quantum world, observation seems to help decide what becomes real. Feynman emphasized that this is not a philosophical add-on or a poetic metaphor. It is forced upon us by experiments. We cannot escape it by clever language or better instruments. Many people try to soften this discomfort by saying that quantum effects only apply to tiny particles, not to the real world we live in. But this belief is also misleading. The reason we do not see quantum weirdness in everyday life is not because it disappears, but because it averages out. The underlying rules are still there. The universe, at its most fundamental level, does not behave according to classical intuition. Our everyday experience is a simplified approximation, not the truth. Feynman's keynote challenges another deeply held belief, that scientific progress always moves toward clarity. We assume that as theories improve, mysteries shrink. Quantum mechanics defies this expectation. It is one of the most successful theories ever created, yet it leaves us with deeper conceptual confusion than the theories it replaced. This creates a strange tension. How can a theory be so successful and yet so unsatisfying at the same time? Feynman's answer was honest and unsettling. Nature is not obligated to make sense to us. Our desire for clear pictures and intuitive explanations is a human preference, not a universal law. Quantum mechanics works, not because it matches our intuition, but because nature behaves that way. The mystery persists because our minds evolved to understand a world of rocks, trees, and predators, not probability waves and superpositions. This realization forces us to confront the limits of human understanding. The keynote is not merely about physics. It is about humility. Feynman was challenging the belief that intelligence alone can conquer all mysteries. Even the smartest physicists, armed with powerful mathematics, are still confused when they try to explain what quantum mechanics says about reality. The confusion is not a temporary gap waiting to be filled. It may be a permanent feature of how the universe works. This idea is deeply uncomfortable because it clashes with the narrative of scientific triumph. We like stories where mysteries are solved and knowledge steadily increases. Feynman's keynote suggests a different story. Knowledge can increase while understanding remains incomplete. We can know how without knowing why. We can predict outcomes without knowing what is actually happening between observations. The challenge becomes even sharper when we consider how casually people talk about quantum mechanics today. The word quantum is often used as a symbol of mystery, magic, or hidden power. Feynman strongly disliked this misuse. He did not see quantum mechanics as mystical. He saw it as brutally honest. The mystery was not spiritual or vague. It was precise, mathematical, and unavoidable. By calling it the deepest mystery, Feynman was also warning against false confidence. Many interpretations of quantum mechanics attempt to restore classical intuition by adding hidden variables, multiple universes, or special roles for consciousness. Some of these ideas are mathematically consistent. Others are speculative, but none have resolved the mystery in a way that satisfies everyone. The disagreement itself is telling. When experts cannot agree on what a theory means, it signals that something fundamental is at stake. This keynote also challenges the belief that reality must be visualizable. We like to imagine particles as tiny balls or waves as ripples in water. Quantum mechanics resists such imagery. Any picture we create eventually breaks down. Feynman repeatedly warned students not to demand visual explanations where none exist. The equations are not hiding a simple picture behind them. The equations are the final description. For many people, this feels like a failure. If we cannot picture reality, how can we claim to understand it? Feynman turned this question around. Understanding, he argued, does not require comfort. It requires accuracy. If reality is strange, then honest understanding must accept that strangeness. The mystery is not a flaw in the theory. It is a feature of the universe. At a deeper level, this keynote challenges our belief in certainty. Classical physics promised a deterministic universe where the future could be predicted exactly if we knew the present precisely. Quantum mechanics breaks this promise. Even with perfect knowledge of a system, only probabilities can be predicted. This randomness is not due to ignorance. It is built into the fabric of reality. Feynman found this especially troubling and fascinating. Randomness at a fundamental level means the universe is not a clockwork machine. Events happen without definite causes in the classical sense. This idea shakes the foundations of how we think about causality, responsibility, and order. It forces us to accept that uncertainty is not just a practical limitation, but a fundamental principle. The keynote's power lies in how quietly radical it is. Feynman was not shouting about mystery for dramatic effect. He was calmly stating a fact based on decades of experimental evidence. The mystery remains because every attempt to remove it either contradicts experiments or replaces it with something even stranger. This persistence is what makes it the deepest mystery. By challenging common beliefs, Feynman was inviting a new kind of scientific maturity. Instead of demanding comforting explanations, he encouraged acceptance of confusion as a sign of honesty. To say we do not know what it means is not a weakness. It is a recognition of reality's complexity. This perspective also changes how we see the role of science in human life. Science is not a machine for producing certainty. It is a method for producing reliable predictions and disciplined doubt. The deepest mystery reminds us that even our best theories can leave us intellectually unsettled. And perhaps that is not a problem to be solved, but a truth to be lived with. In this sense, Feynman's keynote is not pessimistic. It is liberating. It frees us from the illusion that everything must make sense in familiar terms. It allows wonder to survive alongside knowledge. The universe does not owe us simplicity, and yet it gives us patterns we can use, technologies we can build, and questions that keep us searching. This challenge to common belief is why the mystery endures. It is not hidden in technical details or obscure experiments. It is right at the surface, confronting our expectations about what science should be. The deeper we look, the clearer it becomes that the mystery is not about quantum mechanics being hard. It is about reality being different from what we imagined. When the mystery of physics is described as being rooted in observation rather than equations, it immediately overturns another comfortable assumption. We are used to believing that the deepest problems in science are mathematical. Difficult equations, abstract symbols, and complex calculations seem like natural hiding places for mystery. If only the math were simpler, we think, understanding would follow. Richard Feynman's second keynote quietly dismantles this belief by pointing out that quantum mechanics is mathematically precise and experimentally flawless, yet conceptually disturbing. The mystery does not hide in the symbols on the page. It emerges the moment we try to connect those symbols to what we actually see. Observation sounds like an ordinary word. In everyday life, it feels passive and harmless. We look at something, and it reveals itself. The act of seeing seems separate from the thing being seen. Classical physics adopted this assumption without hesitation. Measurement, in that framework, is a window into reality. It does not disturb the system in any fundamental way. At worst, it introduces small errors that can be corrected with better instruments. Quantum physics refuses to cooperate with this picture. Observation is not a neutral act. It is an interaction, and that interaction changes what is observed. This is not a philosophical opinion, but an experimental fact. When physicists measure the position of a particle, its momentum becomes uncertain. When they measure which path it takes, interference patterns vanish. The results depend not only on the system itself, but on how we choose to observe it. Feynman emphasized that this dependence is not due to clumsy instruments or human limitations. Even in idealized experiments, observation alters outcomes. The mystery, therefore, is not technological. It is structural. Nature itself seems to behave differently when observed. This realization forces a shift in how we think about reality. Instead of a world that exists fully formed and waits to be discovered, we encounter a world that responds to our questions. This idea feels deeply unsettling because it blurs boundaries we rely on. We want a clear separation between the observer and the observed, between subject and object. In everyday experience, this separation works well. A thermometer measures temperature without becoming part of the weather. A camera records a scene without changing it in any meaningful way. Quantum mechanics breaks this comforting division. In the quantum realm, measuring devices cannot be ignored. They are not external spectators. They are participants. When a particle interacts with a detector, both are altered. The particle's quantum state changes, and the detector records a definite outcome. This interaction is unavoidable. There is no way to just look without touching. The double-slit experiment captures this mystery with brutal clarity. When particles pass through two slits without being observed, they produce an interference pattern suggesting wave-like behavior. When detectors are placed to observe which slit each particle passes through, the interference disappears. The particles behave differently depending on whether observation occurs. The equations predict this perfectly. The mystery lies in why nature cares about our observational choices. Feynman was careful not to say that human consciousness causes this change. That idea is tempting, but it is not supported by evidence. Observation in quantum mechanics does not require a mind watching. It requires interaction. A detector, a screen, or even the environment itself can play the role of observer. Yet this clarification does not dissolve the mystery. It deepens it. If observation is just interaction, why do certain interactions produce definite outcomes while others preserve quantum uncertainty? This question leads to the heart of the problem. Quantum systems evolve smoothly and predictably according to mathematical rules when they are not observed. Their behavior is described by waves of probability. But when an observation occurs, this smooth evolution seems to break. Probabilities suddenly collapse into a single result. The equations do not clearly explain how or why this happens. They tell us how to calculate the probabilities of outcomes, not how one outcome becomes real. This sudden change is often called the measurement problem, but Feynman resisted treating it as a technical glitch. He saw it as a fundamental feature of nature. The mystery is not that we lack a better equation. It is that our basic concepts of observation and reality are misaligned with how the universe behaves. The role of observation also challenges the idea of objective truth. In classical physics, different observers might describe a system differently, but there is an underlying reality they all refer to. In quantum mechanics, different experimental setups can reveal mutually exclusive aspects of a system. Measuring position and measuring momentum are not just difficult to do simultaneously. They are fundamentally incompatible. The system does not possess both properties in a definite way at the same time. This forces us to reconsider what it means for something to be real. If a property cannot be observed without destroying another property, does it exist at all before measurement? Feynman was not comfortable with easy answers to this question. He preferred to acknowledge the discomfort rather than mask it with philosophical speculation. The mystery is not solved by choosing a particular interpretation. It remains no matter which story we tell. Another unsettling implication is that observation introduces irreversibility. Quantum evolution without measurement is reversible. Given complete information, one can run the equations forward or backward in time. Measurement, however, produces a definite outcome and leaves a permanent record. Once a detector clicks, the system cannot be returned to its previous state. This irreversible jump stands in contrast to the smooth, reversible laws governing unobserved quantum systems. This break between reversible evolution and irreversible observation hints at a deeper connection between quantum mechanics and time itself. Why should observation introduce an arrow of time? The equations alone do not answer this. Once again, the mystery is not mathematical, but conceptual. Observation appears to do something special that the equations merely describe without explaining. Feynman's keynote also exposes the limits of reductionism. We often believe that if we analyze a system into smaller and smaller parts, understanding will improve. Quantum mechanics complicates this idea. The behavior of a quantum system cannot always be understood by studying its components in isolation. Observation ties the system to its environment, creating correlations that cannot be ignored. This interconnectedness means that reality at the quantum level is not simply out there, waiting to be dissected. It is relational. What can be said about a system depends on how it interacts with something else. Observation is one form of interaction, but it is a particularly revealing one because it forces a choice among possibilities. The mystery rooted in observation also reshapes our view of scientific explanation. Traditionally, explanation meant telling a causal story. This happened because that happened. Quantum mechanics resists such narratives. We can say why certain probabilities arise, but we cannot say why a particular outcome occurs in an individual event. Observation selects an outcome, but it does not explain why that outcome and not another one became real. Feynman accepted this limitation with unusual clarity. He did not pretend that better language or deeper intuition would eliminate it. Instead, he urged physicists to be honest about what the theory does and does not provide. The deepest mystery, in this view, is not ignorance waiting to be corrected, but a boundary where explanation gives way to description. This boundary challenges the belief that science must always provide meaning in addition to prediction. Quantum mechanics provides reliable predictions and astonishing technological power. Yet when we ask what observation really does, we reach a point where words fail. The theory functions without offering a satisfying story. The discomfort created by this realization has driven decades of debate. Some interpretations try to remove the special role of observation by proposing many parallel realities. Others modify the equations to eliminate sudden collapse. Still, others argue that observation is simply an emergent phenomenon arising from complex interactions. Each approach shifts the mystery rather than eliminating it. The fact that no consensus exists underscores Feynman's point. The mystery is not hiding in the math. It is embedded in the act of observation itself. This keynote ultimately invites a change in attitude. Instead of treating observation as a passive act, we must recognize it as a fundamental part of how nature reveals itself. Reality is not fully defined independently of how it is probed. This does not mean that reality is subjective or arbitrary. It means that the universe has rules about what can be known and how it can be known, and those rules are stranger than our classical intuitions. By grounding the mystery in observation, Feynman was reminding us that physics is an experimental science at its core. Equations guide us, but experiments confront us with facts that defy simple interpretation. The deepest mystery is not that the equations are hard, but that the simple act of looking changes what we see. This realization leaves us in a peculiar position. We can build devices that manipulate quantum systems with extraordinary precision. We can harness observation itself as a tool, turning measurement into technology. Yet we remain uncertain about what observation truly means. The mystery persists not because we lack skill or intelligence, but because the universe does not conform to our expectations of detached observation. In this sense, the second keynote reinforces Feynman's broader message. The deepest mystery in physics is not hidden in some distant, inaccessible corner of theory. It sits at the very center of our interaction with nature. Every measurement, every observation, quietly reminds us that the universe is not just something we look at. It is something we participate in. When quantum behavior forces us to rethink reality itself, the disturbance goes far deeper than scientific technique or experimental detail. It reaches into the foundations of how humans have always understood existence. For most of history, reality was assumed to be solid, definite, and independent of us. Mountains existed whether anyone climbed them or not. Stars burned in the sky long before humans looked up. Physics, in this view, was the discipline that described an already existing world. Quantum theory disrupts this assumption so thoroughly that even the meaning of the word real becomes uncertain. At first glance, this seems exaggerated. After all, the world around us still looks solid and stable. Tables do not flicker in and out of existence. Objects do not appear in multiple places at once. Yet quantum mechanics insists that, at the most fundamental level, reality does not behave this way. The solidity we experience is not fundamental. It is an emergent effect, a large-scale illusion created by countless microscopic events obeying rules that are deeply unlike our everyday intuitions. In classical thinking, reality is made of things with properties. A particle has a position, a speed, and a trajectory. Even if we do not know these values precisely, we assume they exist. Ignorance is seen as a limitation of knowledge, not a feature of reality. Quantum mechanics breaks this assumption. It does not say that we simply lack information about particles. It says that certain properties do not exist in a definite form until they are measured. This idea is profoundly unsettling because it undermines the notion of an objective world fully formed beneath our observations. Instead of particles having precise attributes, they are described by probability waves. These waves do not represent ignorance about hidden facts. They represent all that can be meaningfully said about the system. Reality, at this level, is not a list of definite facts, but a structured set of possibilities. Feynman emphasized that this is not philosophical decoration. It is forced upon us by experiment. When electrons are sent one by one through an apparatus, they do not behave like tiny billiard balls following well-defined paths. They behave like spread-out waves interfering with themselves. Yet when detected, they appear as localized impacts, as if they were particles all along. The same entity seems to be both wave and particle, depending on how we interact with it. This dual behavior is not merely confusing. It challenges the very idea that objects have an independent nature. In classical physics, how we observe something does not change what it is. In quantum physics, how we observe something helps determine what it becomes. Reality is not simply revealed by measurement, it is shaped by it. This leads to a deeper question. What does it mean for something to exist if its properties are not fixed? Quantum theory suggests that existence itself is probabilistic. Before measurement, A system exists in a superposition of possibilities. These possibilities are not hypothetical guesses. They have real, measurable consequences. Interference patterns arise because all possibilities coexist and interact. The idea that multiple possibilities are simultaneously real, even temporarily, strains language to its breaking point. We are accustomed to thinking in terms of either, or. Either the particle went left or it went right. Quantum mechanics insists on both, and, at least until observation forces a choice. This is not a failure of description. It is a reflection of how nature behaves. When Feynman pointed to this as part of the deepest mystery, he was highlighting how quantum mechanics refuses to fit into classical categories. We try to imagine particles as tiny objects or waves as ripples in space, but neither picture fully works. Any mental image we construct captures part of the truth and then collapses under closer scrutiny. This failure of imagery has serious consequences. Much of human understanding relies on visualization. We understand by forming mental models. Quantum mechanics denies us a complete model. It offers equations that work and predictions that succeed, but no simple picture of what is really happening. Reality becomes something we can calculate, but cannot comfortably imagine. This disconnect forces us to confront the possibility that reality is not obligated to match human intuition. Our intuitions evolved for survival at human scales, not for understanding the foundations of the universe. Quantum mechanics exposes the limits of those intuitions with ruthless clarity. It tells us that reality is stranger than we expect, not because it is complicated, but because it is fundamentally different from the world our senses evolved to navigate. The rethinking of reality also affects our understanding of causality. In classical physics, causes produce effects in a clear, deterministic chain. If you know the initial conditions, you can predict the outcome. Quantum mechanics breaks this chain. Even with complete knowledge of a system's quantum state, only probabilities can be predicted. Individual events occur without definite causes in the classical sense. This randomness is not due to hidden factors we have yet to discover. It is built into the theory. Reality itself appears to be indeterminate. This challenges the belief that the universe is a perfectly ordered machine running on strict rules. Instead, it suggests a universe where chance is fundamental. For many, this is deeply troubling. Determinism offers comfort. It implies that the universe is predictable and rational. Quantum randomness feels like a betrayal of that promise. Yet experiments leave little room for doubt. Random outcomes are not signs of ignorance. They are features of reality. Feynman accepted this conclusion with characteristic honesty. He did not try to soften it by appealing to hidden mechanisms or comforting interpretations. He acknowledged that nature simply does not behave the way we expect. The deepest mystery is not that this behavior is hard to calculate, but that it forces us to abandon cherished assumptions about how reality must work. The challenge extends further when we consider identity. In the classical world, objects are distinct individuals. One particle is different from another, even if they are similar. Quantum mechanics undermines this distinction. Fundamental particles of the same type are truly identical. They are not merely similar, they are indistinguishable in principle. Swapping two electrons produces no observable difference. This indistinguishability has real physical consequences. It shapes the structure of atoms, the stability of matter, and the behavior of solids. Reality at the quantum level does not consist of individual objects with unique identities. It consists of patterns, relationships, and collective behaviors. This forces a rethinking of what it means to be an object at all. Reality also becomes deeply relational. Properties are not absolute. They depend on interactions. A particle's position is defined relative to a measuring device. Its energy is defined relative to a reference frame. This relational nature is not new to physics, but quantum mechanics pushes it to an extreme. There is no view from nowhere. There is no complete description of reality independent of context. This idea challenges the notion of a single, objective reality described from a detached perspective. Instead, quantum mechanics suggests a layered reality, where what can be said depends on how questions are asked. This does not mean that reality is subjective or arbitrary. It means that reality has structure, and that structure limits what can be simultaneously known. Feynman was particularly sensitive to the temptation to overinterpret these ideas. He warned against turning quantum mechanics into metaphysics or mysticism. The mystery is not an invitation to vague speculation. It is a precise, experimentally grounded challenge to our concepts. The task is not to escape the mystery, but to respect it. This respect requires intellectual discipline. It requires resisting the urge to force quantum behavior into familiar categories. When we say that a particle is both a wave and a particle, we are not solving the mystery. We are admitting that classical language fails. The reality described by quantum mechanics does not fit neatly into our words. The rethinking of reality also affects our sense of time. In classical physics, time flows smoothly and events occur in sequence. Quantum mechanics introduces phenomena where time behaves strangely. Certain processes appear reversible until observation occurs. Others involve correlations that do not respect classical notions of temporal order. Reality becomes less like a story unfolding and more like a network of relationships. All of this contributes to the feeling that quantum mechanics is not just a theory about small things, but a theory that reshapes our world, you. It forces us to accept that reality is not made of solid facts, but of probabilities, interactions, and constraints. What exists is not a collection of definite properties, but a structure of potential outcomes. This realization can feel destabilizing. If reality itself is uncertain, what does that say about knowledge, truth, and meaning? Feynman did not offer comforting answers. He believed that the role of physics was not to provide existential reassurance, but to describe nature honestly. If reality is strange, then honest thinking must be strange as well. Yet there is a quiet strength in this position. By accepting that reality does not conform to our expectations, we free ourselves from false certainty. We learn to live with uncertainty not as a failure, but as a feature of the universe. The deepest mystery becomes a source of humility rather than despair. Quantum behavior does not tell us that reality is unknowable. It tells us that reality is knowable in a different way. We can know probabilities, patterns, and constraints. We can build technologies that work with astonishing precision. But we may never have a simple story that makes reality feel comfortable. Feynman saw this not as a defeat, but as an invitation to wonder. The universe is not required to make sense in human terms. It only has to be consistent with itself. Quantum mechanics reveals a reality that is internally coherent, experimentally confirmed, and conceptually shocking. This shock is not something to be resolved quickly. It is something to be carried. The rethinking of reality demanded by quantum behavior is ongoing. Each generation of physicists inherits the same equations and the same mystery. The calculations improve, the experiments grow more precise, but the fundamental questions remain. In this sense, the third keynote captures the heart of Feynman's insight. The deepest mystery in physics is not hidden behind layers of technical difficulty. It is exposed the moment we ask what reality is really like. Quantum mechanics answers that question not with clarity, but with a challenge. Reality is not what you thought it was, and understanding it will require letting go of ideas that once felt obvious. The mystery endures because it is not a gap in knowledge waiting to be filled. It is a confrontation with the limits of human intuition. Quantum behavior forces us to rethink reality itself, and that rethinking has no final endpoint. It is a permanent feature of living in a universe that is stranger, richer, and more subtle than we ever imagined. The idea that measurement plays a central role in shaping physical outcomes strikes at the very heart of how science has traditionally understood its task. For centuries, measurement was seen as a passive act, a way of uncovering facts that already existed. A ruler reveals length, a clock reveals time, a scale reveals weight. The world, in this view, is fully formed and waiting to be read. Quantum physics dismantles this assumption with quiet but relentless force, and in doing so, it reveals one of the most unsettling insights in all of science. The outcomes we observe are not merely revealed by measurement, they are, in a fundamental way, created by it. This does not mean that reality is imaginary or that nature bends to human will. The universe is not subjective in a casual sense, but it does mean that the classical separation between what exists and how we know it breaks down at the quantum level. Measurement is no longer a neutral window. It is an active process that participates in the event it records. The outcome of an experiment depends not only on the system under study, but on the very act of measuring it. At first, this sounds like a technical complication, something that might disappear with better instruments or more refined techniques. But decades of experiments have shown that this is not the case. Even in idealized situations, measurement changes the system in an unavoidable way. This is not a flaw of our tools. It is a feature of nature itself. Quantum systems evolve smoothly when left alone. Their behavior is described by precise mathematical rules that allow probabilities to be calculated with extraordinary accuracy. Yet when a measurement is made, something dramatic happens. The smooth evolution halts, and a single, definite outcome appears. A particle is detected here, not there. A spin is measured as up, not down. This sudden transition is not described by the same equations that govern the system's evolution. Instead, it is introduced as a separate rule, one that tells us how probabilities turn into facts. This gap between evolution and outcome is where the central mystery of measurement lies. The theory tells us how to calculate probabilities, but it does not tell us how one possibility becomes real. The moment of measurement stands apart, unexplained yet essential. Without it, quantum mechanics cannot connect its abstract probabilities to the concrete world of experience. Richard Feynman was deeply troubled by this. He understood the mathematics as well as anyone, yet he repeatedly emphasized that the equations do not explain what measurement actually does. They describe its consequences, not its mechanism. This honesty is what makes the mystery so powerful. The deepest questions are not hidden in obscure corners of theory. They appear at the very moment we ask how an experiment produces a result. The role of measurement also challenges our understanding of cause and effect. In classical physics, causes precede effects in a clear chain. Measurement simply records what the cause has already produced. In quantum physics, the relationship is less straightforward. The choice of what to measure can influence which outcomes are even possible. Measuring position makes momentum uncertain. Measuring one property excludes the possibility of knowing another. The act of measurement shapes the landscape of reality rather than merely mapping it. This does not mean that physicists can manipulate outcomes at will. The probabilities are fixed by the theory. Measurement does not allow control over which outcome occurs in a single event. What it does control is the framework within which outcomes can occur. The structure of the experiment determines the kinds of facts that can come into existence. One of the most striking aspects of this is that measurement introduces definiteness into a world of possibilities. Before measurement, a quantum system exists in a superposition, a combination of all possible states allowed by the theory. These states are not imaginary, they have real physical effects, such as interference, yet none of them is singled out as the actual outcome. Measurement forces a choice. One possibility becomes real, and all others vanish from observation. This process feels almost violent in contrast to the gentle, predictable evolution that precedes it. The system goes from being spread out over many possibilities to being locked into a single fact. The theory does not explain how this happens. It simply tells us that it does. Measurement is treated as a primitive concept, something that cannot be reduced to simpler terms within the theory itself. This creates a profound tension. Physics aims to explain complex phenomena in terms of simpler ones. Yet here we encounter a process that resists explanation. Measurement is essential, but it stands outside the smooth flow of physical law. It is both part of physics and strangely beyond it. The centrality of measurement also raises uncomfortable questions about objectivity. If outcomes depend on measurement, can there be a reality independent of observation? Quantum mechanics does not deny reality, but it redefines it. Reality is not a collection of pre-existing facts. It is a structured set of potential outcomes, constrained by physical laws and realized through interaction. This view forces us to abandon the idea that the world is fully specified at all times. Instead, the world becomes something that crystallizes through events. Measurement is one such event, a moment where potential becomes actual. This does not mean that observers create reality out of nothing. It means that reality unfolds in stages, with measurement playing a decisive role in that unfolding. The discomfort this causes is easy to understand. We want the universe to be there whether or not we look at it. Quantum mechanics does not fully deny this desire, but it complicates it. Certain aspects of reality may exist only as possibilities until they are measured. This is not a failure of knowledge. It is a statement about how nature works. Measurement also introduces irreversibility into quantum physics. The equations that describe unmeasured systems are reversible in time. In principle, they can be run backward. Measurement, however, produces a permanent record. Once an outcome is registered, it cannot be undone. The system cannot be returned to its prior superposition. Information is lost in a way that cannot be reversed. This irreversible character of measurement connects quantum mechanics to deeper questions about time and entropy. Why should measurement break time's symmetry? Why should it create an arrow of time? These questions remain open, and they underline how central measurement is to our understanding of physical reality. Measurement is not just another interaction. It marks a boundary between possibility and fact. Another unsettling feature is that the theory does not specify precisely what counts as a measurement. Is it the interaction with a detector, the amplification of a signal, the recording of a result? Different interpretations answer differently, but the ambiguity itself is revealing. Measurement is not sharply defined within the theory, yet its effects are unmistakable. This ambiguity has led to decades of debate. Some physicists argue that measurement is simply a complex physical interaction that we do not yet fully understand. Others suggest that it is fundamentally different from ordinary interactions. Still others try to eliminate the special role of measurement altogether by proposing alternative frameworks. None of these approaches has achieved universal acceptance. Feynman's perspective was pragmatic but unsparing. He acknowledged that we use the concept of measurement because it works. It allows us to connect theory to experiment. But he refused to pretend that this use amounts to understanding. The deepest mystery is not that measurement is complicated. It is that measurement seems to do something no other physical process does. It turns probabilities into realities. This realization changes how we think about experiments. An experiment is not just a test of a theory. It is a process that helps bring specific outcomes into being. The design of the experiment matters not only for accuracy, but for reality itself. Different experimental arrangements do not merely reveal different aspects of the same underlying facts. They can produce fundamentally different facts. This does not mean that reality is arbitrary or dependent on human whim. The rules governing probabilities are strict. The outcomes are constrained, but within those constraints, measurement plays an active role. It selects which questions nature is allowed to answer. The central role of measurement also challenges the idea that physics describes what is happening between observations. Quantum mechanics allows us to calculate probabilities for future measurements based on past ones, but it resists giving a clear account of what exists in the meantime. The concept of a continuous, observer, independent reality becomes difficult to maintain. This gap between measurements is not empty, but it is not easily described. The system exists in a state defined by probabilities, not facts. Measurement punctuates this continuous evolution with discrete events. Reality, at the quantum level, is not a smooth narrative. It is a sequence of potentialities interrupted by acts of measurement. For many, this feels incomplete. A theory that cannot describe what is happening between observations seems unsatisfactory. Yet every attempt to fill this gap introduces new problems. Hidden variables conflict with experiments. Multiple realities strain plausibility. Modified equations raise unanswered questions. The persistence of these difficulties suggests that the problem lies not in the theory, but in our expectations. Measurement forces us to accept that the universe may not offer the kind of story we want. It may offer rules without pictures, predictions without narratives. The outcomes exist, the probabilities work, but the underlying process remains opaque. This does not diminish the power of quantum mechanics. On the contrary, it highlights its strange success. Technologies based on quantum measurement are now routine. We manipulate individual atoms, detect single photons, and build devices whose operation depends on measurement itself. We use the mystery as a tool, even as we struggle to understand it. The central role of measurement also invites humility. It reminds us that our theories are not mirrors of reality, but frameworks for interacting with it. Measurement is where theory meets world, and that meeting is not passive. It is creative, transformative, and irreversible. Feynman's insistence on facing this mystery directly is what gives his insight lasting power. He did not offer comforting interpretations. He did not claim that the problem would soon be solved. He simply stated that measurement sits at the center of quantum mechanics, shaping outcomes in a way we do not fully understand. This honesty forces us to reconsider what it means to explain something in physics. Perhaps explanation does not always mean reducing phenomena to simpler mechanisms. Perhaps sometimes it means clearly stating the limits of what can be said. Measurement marks such a limit. The universe, as revealed by quantum mechanics, is not a static collection of facts. It is a dynamic interplay of possibilities and events. Measurement is the bridge between these two realms. It is where potential becomes actual, where probability becomes experience. This does not mean that measurement is mystical or beyond science. It means that it is fundamental. It cannot be derived from deeper principles without changing the theory itself. It is a basic feature of how the world works. In accepting this, we are forced to rethink our relationship with reality. We are not detached observers looking in from the outside. We are participants in a process where questions and answers are inseparable. Measurement is the moment where this participation becomes unavoidable. The fourth keynote thus reveals a universe where outcomes are not simply waiting to be discovered. They emerge through interaction. Measurement is not the end of physics. It is the point where physics touches reality, and in that touch, something new is born. This is why the mystery remains so deep. It is not a puzzle waiting for a clever solution. It is a feature of a universe that refuses to separate what happens from how it is known. Measurement shapes outcomes, and in doing so, it reshapes our understanding of what it means for something to be real. The fact that this mystery remains unresolved even today is not a sign of failure, but one of the most remarkable and humbling aspects of modern physics. After more than a century of intense effort, countless experiments, and extraordinary technological progress, the core puzzle at the heart of quantum mechanics still stands. We can predict outcomes with astonishing precision, manipulate quantum systems with breathtaking control, and build technologies that would have seemed like science fiction to earlier generations. Yet when we ask what the theory truly says about reality, the answers fragment, diverge, and often contradict one another. The mystery endures, not because physicists are careless or unimaginative, but because nature itself resists the kind of explanation we are accustomed to. This persistence challenges a deeply ingrained belief about scientific progress. We are used to thinking that unresolved questions are temporary. History seems to support this view. Mysteries of planetary motion gave way to Newton's laws. The nature of light became clearer with Maxwell's equations. The structure of atoms emerged through quantum theory itself. Each time, confusion appeared to shrink as understanding grew. It feels natural to expect the same pattern here, and yet, quantum mechanics defies it. The theory works almost too well. Its predictions have been tested to extraordinary accuracy, often to many decimal places. Experiments confirm its results again and again. There is no serious doubt that quantum mechanics is correct within its domain. This creates a strange situation. The most successful theory in the history of science is also one of the least conceptually understood. The unresolved mystery does not lie in whether the theory works, but in what it means. This gap between success and understanding has led to a proliferation of interpretations. Each interpretation attempts to explain the same mathematical formalism in a different conceptual language. Some propose that all possible outcomes occur, each in its own branching reality. Others suggest that hidden variables determine outcomes in ways we cannot access. Still others modify the equations themselves, introducing new dynamics to explain how probabilities become facts. There are interpretations that emphasize information, others that emphasize relationships, and some that deliberately avoid saying anything about reality at all. The sheer number of competing interpretations is itself a clue. In most areas of physics, disagreements fade as evidence accumulates. Here, evidence supports the equations, but not the stories we tell about them. All major interpretations reproduce the same experimental results. None can be decisively confirmed or ruled out by existing experiments. The mystery remains untouched by empirical success. This situation would have disturbed Feynman deeply, and indeed it did. He was skeptical of interpretations that promised more understanding without delivering testable predictions. For him, the unresolved nature of the mystery was not an embarrassment to be hidden, but a fact to be acknowledged. Pretending that we understand quantum mechanics at a deeper level than we do would be dishonest. The endurance of the mystery also reveals something important about the limits of scientific explanation. Physics excels at describing patterns and predicting outcomes. It does this through mathematical structures that capture regularities in nature. But explanation, in the sense of providing a clear mental picture of what is happening, may not always be possible. Quantum mechanics suggests that prediction and explanation can come apart. This separation is unsettling because it forces us to revise our expectations of science. We often assume that understanding means being able to imagine how something works. If we cannot picture it, we feel unsatisfied. Quantum mechanics denies us this comfort. It offers equations without images, rules without narratives. The unresolved mystery is a reminder that the universe does not owe us intuitive stories. The persistence of the mystery also highlights the role of language. Our everyday language evolved to describe a world of solid objects and definite events. We speak in terms of things happening at places and times, caused by other things. Quantum phenomena do not fit easily into this framework. When we try to describe them, we are forced to stretch words beyond their usual meanings. Terms like particle, wave, measurement, and state become ambiguous, overloaded, and sometimes misleading. This linguistic strain is not accidental. It reflects a deeper conceptual mismatch. The world described by quantum mechanics is not organized around the categories our language assumes. The unresolved mystery persists in part because we lack the conceptual tools to articulate what the theory implies about reality. New mathematics helps us calculate, but new concepts are harder to come by. Another reason the mystery remains is that quantum mechanics sits at the foundation of all physical description. There is no deeper, more familiar theory beneath it to anchor our intuition. In classical physics, unfamiliar phenomena could often be explained in terms of underlying mechanisms. Molecules explained gases, atoms explained chemistry. Quantum mechanics, however, is the level at which explanation seems to stop. We reach a point where we can describe behavior, but not reduce it to something more intuitive. This creates a sense of finality that is uncomfortable. It suggests that the unresolved mystery may not be a temporary gap in knowledge, but a permanent feature of the universe. This does not mean that physics will not progress. New theories may emerge, unifying quantum mechanics with gravity or revealing deeper structures. But even such theories may inherit the same conceptual strangeness, rather than eliminate it. The endurance of the mystery also reflects the role of human perspective. Our understanding is shaped by the scales at which we evolved. Quantum phenomena occur at scales far removed from everyday experience. It may be unrealistic to expect our intuitions to adapt fully. Just as we accept that four-dimensional spacetime is difficult to visualize but mathematically consistent, we may have to accept that quantum reality resists complete conceptualization. Yet the mystery is not static. Each generation of physicists revisits it with new tools and fresh perspectives. Experiments probing entanglement, non-locality, and quantum information have deepened the puzzle rather than resolved it. Entangled particles exhibit correlations that cannot be explained by local causes, challenging our notions of separability and independence. These phenomena were once thought to be philosophical curiosities. They are now routinely tested in laboratories. The unresolved nature of the mystery is also evident in how quantum mechanics intersects with other areas of physics. Attempts to reconcile it with gravity have exposed profound conceptual tensions. Space and time themselves may not be fundamental in the quantum realm. If this is true, then the mystery goes even deeper than originally imagined. It may involve the very fabric of reality. Despite this, quantum mechanics continues to be extraordinarily productive. Quantum technologies are advancing rapidly. Computers that exploit superposition and entanglement are being built. Sensors based on quantum principles achieve unprecedented precision. Communication systems harness quantum uncertainty for security. These successes make the unresolved mystery even more striking. We are building a technological future on foundations we do not fully understand. This paradox challenges the idea that understanding must precede application. In the quantum world, application has raced ahead of interpretation. We use the theory because it works, not because we have resolved its deepest questions. This pragmatic success echoes Feynman's attitude. He believed in using theories effectively while remaining honest about their limitations. The unresolved mystery also plays a crucial role in education. Students often expect physics to provide clear answers. Encountering quantum mechanics can be disorienting. The realization that even experts disagree about what the theory means can be unsettling. Yet this uncertainty can also be liberating. It reveals science as a living, evolving endeavor rather than a closed body of facts. This openness invites creativity. New interpretations, new frameworks, and new ways of thinking continue to emerge. Some may eventually gain empirical support. Others may fade. The unresolved mystery keeps the field intellectually vibrant. It prevents complacency and encourages humility. Feynman's insistence on acknowledging this unresolved core was not an admission of defeat. It was a statement of integrity. He understood that pretending to have answers where none exist undermines the credibility of science. By admitting confusion, physicists remain open to discovery. The endurance of the mystery also carries a philosophical lesson. It reminds us that human knowledge has limits. These limits are not always imposed by lack of data or technical skill. Sometimes they arise from the structure of reality itself. Accepting this does not diminish science. It enriches it. The unresolved nature of the deepest mystery also preserves a sense of wonder. In a world where many mysteries have been explained, quantum mechanics stands as a reminder that the universe is not exhausted by human understanding. There remains something fundamentally surprising at the heart of reality. This wonder is not abstract. It is grounded in precise experiments and rigorous mathematics. It is not a retreat into ignorance, but an honest confrontation with what we do not know. The mystery remains because every attempt to eliminate it either contradicts evidence or replaces it with something equally strange. In this way, the unresolved mystery becomes a mirror reflecting our expectations back at us. We expect the universe to be intuitive, deterministic, and fully describable. Quantum mechanics quietly refuses these expectations. It works without satisfying them. The persistence of the mystery also shapes the future of physics. It motivates new experiments designed to probe the foundations of the theory. It inspires efforts to develop new conceptual frameworks. It encourages dialogue between physics, philosophy, and mathematics. The unresolved question is not an endpoint, but a driving force. Ultimately, the fact that the deepest mystery in physics remains unresolved even today is a testament to the depth of the universe. It suggests that reality is richer than any single theory can capture in human terms. We may refine our equations, expand our experiments, and deepen our understanding, but some aspects of reality may always resist full comprehension. Feynman understood this, and he embraced it. For him, the beauty of physics lay not in the illusion of certainty, but in the courage to face uncertainty honestly. The unresolved mystery is not a flaw to be corrected. It is a feature of a universe that continues to surprise us. This enduring mystery does not close the book on physics. It keeps it open. It reminds us that knowledge is not a final destination, but an ongoing journey. The deepest mystery remains, not as a failure of science, but as a sign of how far science has taken us, and how much remains beyond our grasp.